The global internet was built to survive as a sprawling web of independent connections, engineered to reroute data through constant flux and unpredictable physical outages. For decades, the foundational protocol of this network, TCP/IP, managed what engineers call north-south traffic. This is data moving between external users and servers across a wide area network where individual computers are loosely connected and acting independently. But modern data centers have evolved away from that model. They operate as a single, unified AI factory, defined instead by east-west traffic. Rather than serving external web requests, the network handles massive internal communication between thousands of specialized processors. This animated diagram illustrates the operational split. On the left, traditional web traffic moves independently and asynchronously. On the right, the training of large language models requires thousands of graphics processing units to operate in precise, uniform waves. They execute compute cycles in perfect lockstep. In this new environment, basic connectivity is no longer the primary goal. The infrastructure must deliver absolute, continuous synchronization across every piece of hardware. Achieving that level of strict synchronization exposes a severe vulnerability in standard network designs, specifically a phenomenon known as the incast microburst. During AI training, thousands of compute nodes share calculations with a central aggregator simultaneously. This shoots a tidal wave of data, pushing the switch buffer to the bursting point. Because traditional TCP/IP cannot anticipate this influx, the data overloads the switch and shatters the buffer, forcing a packet to drop. Operating on a fail-then-fix loop, the network waits for physical loss before surrounding nodes finally reduce transmission rates. By the time the protocol reacts, the damage is done. The system must trigger a retransmission event to recover that single piece of lost data. Because the graphics processors are tightly coupled, no single processor can move forward until the entire group finishes the current step. The entire parallelized cluster halts, waiting for one tiny packet to clear the network. A millisecond delay for a single packet cascades into widespread computational waste. The failure of reactive networking forces million-dollar compute clusters to sit idle, burning power and time without producing results. To keep these high-density clusters moving, the network must evolve from reacting to failures to actively preventing them. The targeted engineering solution to this bottleneck is the Predictive Tensor Control Protocol, or PTCP. Legacy systems fail under what engineers call the curse of dimensionality. Standard protocols make routing decisions based on isolated variables, looking only at current latency or packet loss, while ignoring the broader physical state of the hardware. This diagram shows how PTCP builds a complete picture. It continuously gathers diverse telemetry from across the entire system. By mapping metrics like PCIe saturation, switch queue depths, and current workload phases along these intersecting axes, it creates a multidimensional state vector, a rigorous mathematical representation of the entire cluster at any given microsecond. By monitoring these interacting variables simultaneously, the protocol calculates the precise statistical likelihood of congestion forming before a switch buffer ever overflows. Processing a probability space of this size introduces a severe engineering hurdle. The sheer volume of data required for a complete system map would quickly overwhelm standard commercial hardware and crash the network. To make this data mathematically tractable, PTCP splits the workload into two distinct operational lanes. This diagram visualizes the first lane, the slow path. Here, the heavy mathematical lifting happens in the background. The massive system state grid is squeezed through a funnel mechanism, breaking the data down into a series of smaller interconnected core blocks. This technique, known as Tensor Train decomposition, shrinks the massive probability space into actionable models without losing the accuracy of the original data. Once optimized, these compact blocks slide directly onto the network hardware. This brings us to the second lane, the fast path. Because the compressed models are incredibly lightweight, they can reside directly on the actual data processing units and network switches managing the traffic. Hosting the logic directly on the data path allows the hardware to evaluate incoming signals and execute anomaly scores in a fraction of a microsecond. Mathematical compression allows the protocol to anticipate incoming traffic spikes. It can preemptively pace data flows and pre-warm memory tiers, keeping the pathways clear so the processing units never have to stop and wait. Deploying autonomous orchestration inside a data center carries inherent risk. An unconstrained predictive model reacting to traffic spikes could accidentally trigger destructive network oscillations, causing the very congestion it was meant to solve. To mitigate this risk, PTCP operates under a governance model shown in this logic diagram, known as the champion-challenger framework, which strictly bounds the protocol's actions. On the left side of the split screen is the live champion model. It executes real-time traffic orchestration, but its decisions are strictly confined by predetermined maximum variance policies, ensuring it can never push the network past safe operational limits. On the right is the quarantined challenger model. It continuously learns new traffic baselines and tests predictions in the background, analyzing live telemetry without any authority to impact actual cluster operations. By stepping away from the reactive survival tactics of the open internet, PTCP provides mathematically bounded determinism. The network transitions from a series of passive pipes into a seamless, proactive extension of the computing hardware itself.